All right, so the plan for today is to finish the linear regression lecture. What's left is trying to demonstrate how to do a multiple linear regression where you're gonna have more than one predictors going on. So if you remember what we had done, we have talked about how to add a single predictor, which is a numerical predictor in our model from the regular normal model. Because the outcome variable being numerical, it's a good idea to use the normal model in the first place. And then from the regular normal model to the regression, really we're just trying to add a predictor in a linear combination in terms of the mean. So we talked about how to do that using the CE consumer expenditure survey example, as we know. We talked about MCMC simulation by JAGS, and also how to do Bayesian inference, talking about how to simulate the fits, how to do predictions, and how to look at the variability and all that. We also spent some time on Wednesday to talk about different ways to give priors. So if you now summarize what we have done, we have talked about 3 different ways to give priors. You can give weakly informative prior. Okay? You can give subjective prior after you do standardization and work on the correlation coefficient. And lastly, for the conditional means, you have certain ways to give the prior, which is what Lab 5 is about. The last part I want to cover for you to get a flavor of the, I guess, the full picture of how to do linear regression is to do a multiple linear regression. So you will see that we're going to start to add more than one predictor, and in particular, different types of predictors. Okay. And then we're also going to cover how to do MCMC simulation and all that. So that will wrap up most of the lecture part of our entire course. So I would say the entire sample that we have over here, I showed you this before, but for the simple linear regression, we were only focused on the log expenditure and log income. So it was the log expenditure being the outcome, and then the log income was the single continuous predictor. But in that data set that we posted on Moodle, you also have the rural or urban status, okay, of the consumer unit. So it is a binary variable. It is the urban-rural status of the consumer unit, 0 if it is an urban CU consumer unit, or 1 if it's a rural CU. Okay? And one more variable that we have in this data set is the race of the reference person of the consumer unit. So we have 6 different categories. So this is a typical categorical variable, and in particular, it is a unordered categorical variable. Okay, so there's no inherent order going on in this variable. So our goal for this part of the lecture is how can we include additional information about the urban-rural status as well as the race category to predict one's outcome, which is the log expenditure. So based on what we talked about before, and many of you have seen regression and multiple linear regression in the past, you will see that we're trying to add them in terms of the linear combination of the expectation that we're able to model. But then, of course, with rural as well as race, that both of them are not numerical anymore. So there are certain careful things that we need to take into account when we're trying to understand how to use them as predictors. Okay, and then of course in the Bayesian context, what are the parameters and how you can give priors to them and how the posterior inference can be done. Okay, so this is overview. Okay. So similar to the simple linear regression, multiple linear regression also assumes an observation-specific mean, which is the mu I over here. So you can see that 42 looks no different from the previous simple linear regression that we're doing. And on this, I actually want to just spend a couple of minutes, also talk quickly about this notation, because some of you are emailing asking about the independence versus IID. Yeah. So independence, as we know, is just saying that, well, the yi's, okay, they are all follow normal distribution. They are different and independent from each other. So that's what this IND stands for. But here we don't do IID because they're only independent but not identical. The reason is because if you look at equation 42, they're independent but not identical because each of the normal has its own mean. So that's why here it's IND but not IID. Okay? But as we know, let's just say, I think when we're talking about the mean chapter, which is early on, we have this IID, normal, mu, mu, and sigma, okay? So here, when we're working with a simple normal model over here, no matter how you give the priors and all that, here it is IID, okay? Because not only the yi's are independent from each other, but they all follow exactly the same normal distribution. So in this case, we have IID. But then the confusion arose, I think, from the email that I got is, if you remember, for the hierarchical model, okay, we have this. So for hierarchical, so J indicates the group, right? And then I indicates the index of the observations in the group. So my question for you, and just 1 minute discussion over here, should we do IID or should we do IND over here? Okay. We used one of them back when we talked about this early on, but I think this caused some confusion. So the question is, here, when all of the yij's follow a normal mu j and sigma, are we talking about independent or are we talking about IID? Let's spend 1 minute on this. And for remote students, I will put you in the breakout room and invite you back in 1 minute. All right, any thoughts? Here, should we do IID or independent? Anyone goes for IID? So I guess everybody else is gonna go with independent. Okay, all right, let's see. So why do you think it's independent instead of IID here? Yes, Shinji?
I don't know, but for Yij, like it's kind of conditional on based on different mu. So like that mu can be like different mu. So I think in that case, like all y's are not necessarily like identical, but they're kind of like independent.
Yeah, I see. Okay, so that's a good point. So another way to write it is what's in blue right now here is the Yij following a normal with mean mu j and sigma is conditioning all the mu j of the group itself and also the sigma. Okay, so if we think about all of the Yij's within the same group, then they're IID. Does that make sense? So if you remember the graphical representation that we used to do, so we have what what do we do? I1, right? And then all of the different groups, yi capital J, right? Capital J is the number of groups, right? When we do the graphical representation, we have our mu1, we have our mu j, right? And then of course we have those hyperparameters that we're gonna do. And down here, we have our sigma contributing to each of the groups over here. Okay, so the question, which I hope now if we're looking at this graphical representation starts to hopefully makes more sense, is that if the Yij over here is talking about all of the Yij's in a particular group, then they follow the same normal because they all have the same normal of mu j and sigma. Okay. But if we're talking about the Yij's across different groups, then they're not following the same, but they're still independent from each other. Okay. So just so you know, if you go back to the hierarchical lecture, I think when I was using this notation, I meant to say the Yij's within the same group, and that's why I put the IID. Okay. So if you were a little bit confused, I guess it totally makes sense. Maybe we were not clear back then that here, this notation of Yij following a normal mu j and sigma, I meant it to be all of the Yij's within the same group. And if it is true, then you can do IID over here. Okay. But just as the graphical representation shows, if we're only talking about observations within the same group, then it's IID. But if I'm talking about one Yij from another Yij from a different group, then they're independent, but not IID. Okay, kind of makes sense now? Okay, all right, good. So now if we come back to what we're doing for this regression context, okay? So clearly we're talking about this mu I, okay? And then because we have an observation specific mu I, so here is independent, but never IID. Okay. All right, so like I said, similar to the simple linear regression, multiple linear regression, we also have an observation-specific mean. And then in addition to using only one predictor, we're going to use multiple predictors to express the mean as a linear combination. So a linear function of, I guess, all possible predictors, and it just depends on what you have in the data. So mathematically, we can write out mu I equals to beta 0 plus beta 1 times the first predictor plus beta 2 times the second predictor up until beta R times the R predictor. So we're going to talk about how we determine, the number of R and everything given the data. But you can think about sometimes we'll write a vector of these bold-faced xi to include the entire vector of all of the known variables for observation I. And then don't forget the betas, even though we can use also a vector to represent it, but they are the parameters that they are unknown. And so later on, we're going to try to give priors to them and do the Bayesian inference. So keep in mind what's known and what is not known. X usually represent the predictors and all that. So it is known, and beta and also the alpha in the past and all that. We usually use Greek letters to represent the unknown quantities. I think not only in Bayesian courses, but in regular frequentist courses as well. But then, of course, for Bayesian methods, for those unknown parameters, we're going to give priors to them and then trying to get their posterior from the Bayesian inference process. Another thing I should mention is that the SI is going to be observation specific. So that vector itself is going to be for observation I, but the betas, they are shared across all of the observations. Okay, so that's the basic assumption of what we're doing when you're constructing a multiple linear regression. The difference compared to before for the simple linear regression is for simple linear, you only have beta 1 plus beta 0 plus beta 1 times the single predictor. Okay, but now you could have multiple going on, and depending on what's available in the data set. Okay, so how can we understand the coefficients? Okay, so when all of the R predictors are continuous, my question for you is, what does beta 0 mean? And what does each beta j mean? So in simple linear regression example, we consider a single predictor to be continuous, and then we talked about the interpretation of the slope, right, which is the beta 1. And now the question is, if all of them are continuous predictors, what will be the intercept mean and what will be each of the slope mean over here? So let's take 2 minutes on this to, well, refresh what we did before and also try to make the extension to a multiple linear regression. And then later we're going to talk about the other types of predictors. All right, so back then what we did is, if it's a single linear regression, we have this, right? And we know that the beta 0, the intercept, means that if my predictor xi takes value 0, my expected outcome, which is the mu I, will be the beta 0 value. Okay? And then my beta 1 is if my numerical predictor xi increases by 1 unit, my outcome, or I should say in this case, the expected outcome, which is the mu I, going to be changed with beta 1 value. Okay? So this is when your xi is a numerical predictor. You're looking at 1 unit change. Okay? So now if we have our predictors and all of them are continuous, the intercept will be something similar, but you just need to make sure that all of the xr's are 0. Okay, so this is the case that when all of the predictors are taking value 0, my intercept equals to the mean, which is the mu I. So that's what the beta 0 means. Okay. On the other hand, for each of the slope, let's just say beta 2 over here. Okay, so for beta 2, because xi2 is once again a numerical or continuous predictor over here, so we're also thinking about 1 unit change, okay, of xi2 going to be associated with beta 2 change in the expected outcome, which is mu I. But don't forget, which is the one subtlety I'm talking about over here, is that because we're doing a multiple linear regression, whenever you're interpreting one slope, you're assuming that all of the other predictors stay unchanged. So we didn't mention it before in a simple linear regression because you only have one predictor going on, so there's nothing to be fixed to be talked about. But if I focused on interpreting beta 2 only, then I need to assume that for a observation that all of the other x's stay unchanged, then I'm looking at x2 changed by 1 unit, and then that is associated with beta 2 change in the outcome. So this is the subtlety I'm talking about. So it's easy to miss that kind of statement and all that. So make sure that you know what's the main difference between simple linear regression to multiple linear regression where we have numerical outcome over here. So in the CE example, however, not all predictors are continuous. Actually, only the log income that we worked on before is continuous. Rural is a binary outcome, a binary predictor, and the race is a categorical predictor with 6 different levels. Okay, so the interpretation will start to change. Okay, once we do not work with continuous predictor, but binary and categorical. And like I said, some of you have experience taking, for example, 242 applied statistical modeling or some other courses in the past that got to talk about the different interpretation and the meaning of the different types of predictor variables. So I think for some of you, this was going to be a review. But if you haven't experienced that before, I think this could be also new to those of you how to deal with binary predictor and categorical predictor. So we're going to talk about the interpretation and of course how to do the inference. So it might be tempting because binary itself is 0 or 1, right? So some people, if not being helpful, to just take it as a numerical predictor and just go about doing it. But the thing is, it is much more common, and I should say correct, to consider it as a binary categorical variable to specifically classify 2 groups. Okay, so when we have 0 equals to urban and 1 equals to rural, instead of thinking about this 0 and 1 as numerical, we should think about it binary and in particular categorical. So we're looking at when all of the observations whose rural is 0, we're looking at the urban group. And then for all of the observations whose rural equals to 1, we're considering them in the rural group itself. Okay? So this kind of classification will eventually put an emphasis on the difference of the expected outcome, which is the mu I, okay, between the 2 groups. So if you consider it as a numerical predictor or continuous predictor, you're thinking about 1 unit change, say from urban to rural, but that unit does not really make sense for a binary outcome. However, if we think about the predictor being a categorical, and then we're thinking about the urban group and the rural group, and if we focus on the comparison between the 2 groups, then the coefficient that we're able to get for the slope over here will tell us the difference of the expected outcome, which is the mu I between the 2 groups. So that's the more common and correct way to think about a binary predictor. So with that in mind, we can actually write out the model a little bit more in detail. Let's consider a simple linear regression, actually, with a single predictor over here, where the predictor is binary. Okay, so let's just say xi is the binary predictor of the rural-urban status. So for the urban group, okay, where xi takes value 0, then mu I just reduces to beta 0. However, when you're looking at all of the observations in the rural group, that is when this xi, the binary variable, takes value 1, you're looking at mu I to be beta 0 plus beta 1. Okay, so you can see that beta 1, which will be the slope that we'll be able to get after we fit the model, is going to show you the difference of the outcome variable, which is mu I, the expected outcome variable mu I, between the urban group and the rural. Okay. So if you are able to simplify, I think, the beta 0 plus beta 1 times xi across the 2 different groups, then you will see what the effect of beta 1 is. And then I think you will see that eventually you represent the change in the expected outcome mu I from the urban group to the rural. The urban group, or whatever when I takes value 0, which is the beta 0 case, a lot of times people also give a name called the reference group. So that is usually when that binary predictor variable takes value 0, okay, because that will be the reference group that you're comparing to. So sometimes you probably have heard about the term reference group. And in our case, it represents the urban group because xi takes value 0 for the urban group. Okay, make sense? Make sense? Okay, yeah, so like I said, I think many of you have seen a version of this in the past. So hopefully not as very surprising as how the model plays out. But what's new here is, as we know, the beta 0 and beta 1, they're unknown. So in the Bayesian framework, we're going to assume that they're random. So we're going to give priors to them and then figure out how to do the MCMC estimation. All right, so let's look at race, which is a unordered categorical predictor. Okay, and we also call it multi-category because it's more than 2 levels. Okay, more than 2 levels compared to the binary over here. So I should also say, just like the binary case, it is common to consider as a categorical variable to classify multiple groups. Okay? So given our application over here, we have 6 different levels in this race variable. If you were to start to do something similar to the binary example that we did before, how many groups do you think there exist? And what are the groups given the outcome? Oh, I should say, given the information about the race variable over here. Okay, so let's pause for 2 minutes on this so you can talk to your neighbors. And for remote students, this is on page 64. All right, anyone wants to offer what you discussed? How many groups should there be for this race categorical predictor, and what are the groups themselves? Anyone? Here or remote?
There's 6 groups.
Mm-hmm.
When you say what are the groups, do you just like each level is a race? Is that what you
Yeah, I
mean?
think
Or
in
do
that
you-
case, right, each level
Yeah.
will be each level, I guess, of the name will just be the group
Yeah.
themselves, right? Yeah, sounds good. Yeah, so we have 6 levels. So indeed, we're gonna have 6 different groups, okay? And just like the binary case, we're gonna have 1 reference group once you do the modeling. I think in R, you can actually choose which one you want, but if you don't, I think the first one is automatically being considered as the reference group, okay? So I agree, I think we're gonna have 6 groups. And then each of the groups corresponds to the level of the race category. And once again, this kind of classification will put an emphasis on the difference of the expected outcome, which is the mu I, once again, between one group that is compared to the reference group. Okay, so all of the changes that we're seeing, each of the slope that we're going to get is referencing, or I should say is referring to the difference between whatever group that we're working at compared to the reference group. Yes, Sarah?
Is like, what if like we choose to be like the reference group? Is that arbitrary?
Yeah, so I was about to say, so I think you can choose which one to be in if you want, if you code it in. But if you don't, I think it's usually the first level that is being coded, which is 1 in this case, going to be considered as the reference level.
But like it doesn't like matter really.
Yeah. So I think the model didn't change.
Okay.
Yeah, between whichever you use as the reference group, but each of the slope gonna have a different meaning. So the estimation, I mean, the results will be different, I guess, when you try to interpret it. But I think at the end of the day, it is still the same model as being fitted. Yeah. Anything else? All right, so we have 6 groups, and then of course is looking at the difference of the expected outcome of mu i's between one group to the reference group, and then mathematically, if you ever want to do it, this is equation 46 is showing you all of the details. Okay, so the reference group, which like I said, if you don't specify it, I think we'll just take the first level as a reference group. So in our case, it's going to be white, and for white, that is when all of the axis over here is taking value 0. Okay, because it's not Black, not Native American, not Asian, not Pacific Islander, and not multi-race. So when all of them are not, you reduce back to beta 0. Okay, and then that is the mu I estimated for the white group. Okay, and then every other group that we're doing over here will be a addition of the slope that you're working with. Okay. So you can see that the labeling and also all of the indexing, we just need to be super careful about how it corresponds to the levels that we actually have in the data. All right, so I guess this hopefully is overall straightforward. The expected outcome mu I for this using the white group based on equation 46 gonna just be beta 0. Okay, because we're looking at the reference group. For Asian group, we know that it's going to be beta 0 plus beta 3, and then beta 5 will be the difference or the change that we'll have for the expected outcome of the multi-race compared to the white race. Okay. The white is being the reference over here, so we're looking at the difference of whatever the group that we're looking at compared to the reference group. Okay, make sense? Yeah, so now I think you start to see that, well, however many levels I have, let's just say K, is the number of levels in the categorical predictor that I'm working with, then the number of slopes, okay, will be K minus 1, because one of them will be the reference level, and we only have the remaining K minus 1 to be compared to the reference level. Okay, make sense? Yeah. All right, so this is how we can look at the binary as a single predictor and the categorical as a single predictor. And then we can now include all of them if we want into the regression analysis as a multiple linear regression. So all of this is going to have its own comparison and all that. Okay, let's take a look. Consider all predictors, just so bear with me of the notation, but I think it's always useful to write it out early on so you know what you're working with and be very careful about everything. Okay, so I'm using standardized value over here. So later on, it's easier to manage all of the calculations and all that. So I use the star sign over here. So mu I star having a intercept, okay? And then I have one contribution from the income, okay, or the log income in this case, okay? And then I have one contribution from the rural. So you see that the rural urban status, because it's binary, so it reduces it to one slope. Okay, because one of them is the reference level. And then I have my beta 3 up to beta 7, all of them, which is 5 of them. So 6 minus 1, that is contributing from my race categorical predictor. So if I'm combining all of this using all of the predictors together, I'm having what we call a multiple linear regression. And the mean mu I is expressed as a linear combination of the intercept and all of the predictors. So if I'm counting, remember we use R as to represent the number of predictors in total, right? In our model. So in this case, R equals to 7. Okay. Even though we start with 3 variables, predictors to start with, but because of the different levels, in particular the ones that we have in the race variable, we end up with 7 slopes. So be very careful about how the model is constructed, and you can also write it out this way. So sometimes people like to just express the mean, but I think for Bayesian context, it's always useful to think about, what are the parameters being conditioned and what are the data being conditioned over here. And then it's useful to write it out as the mean, and then it helps us not to forget about this little sigma. And so when we're doing linear regression, whether it's simple or multiple, there's always this extra sigma as the random variable, a random parameter, I should say, that requires us to give a prior to complete our inference process. Okay. So the number of parameters here, we have beta 0, and then beta 1 to beta 7, so that's 8, right? And then don't forget that sigma, so we have 9 parameters in total. It's a useful practice to think about how many parameters and which are they, because as we know, when you use JAGS, you need to give priors to all of the parameters. So you need to be really careful at counting them and identify them early on so you don't miss them later in the future. Okay? Yes.
When we express the multiple linear regression in a symbolic way, like in this format, do we need to? So within the parentheses, like, should we like write it as a formula, or we can just write it as like from beta 0 to beta 7?
You mean over here?
No, like
in the parentheses over here?
Yeah.
Oh, okay. Yeah, I mean, here I use the parentheses because you can see that the mean is exactly the same as the 47 kind of.
Oh, so basically like you just replace.
Yeah, I replaced the mean with 47.
Yeah, okay.
Yeah, like I said, so I think it's just like for personal preference. I think either one is correct. If you do only 47, I think it only focuses on the mean. And I think for people who are not yet very familiar with all of this modeling, it might be easy to miss that sigma is also a random parameter in the model. So alternatively, you can do 48, which is what I usually do personally. But then of course, if the mean expression gets very complicated, I might just do two two equations or two expressions. But I think the notation of yi, for example, following a normal distribution is always a good practice because then you can see through how many parameters you really have in this model. And like I said, it's very common to miss that sigma. And I should also say, if for those of you who have done linear regression, whether simple or multiple linear regression in the non-Bayesian context, like you use the LM function, right? And then they give you all of the point estimates and standard errors for the slopes and the intercept and all that. So it doesn't really talk much about that sigma, okay? And but so for us in this course to highlight that sigma and all of the betas, they are indeed parameters, and for Bayesian methods we consider them as random. So to me, I feel like it's a good practice to use equation 48, so we know we can see in one just one line, a little bit long, but one line to show all of the parameters in the model. Okay, yeah. So I'm just saying that sigma is easy to be missed, but well, if you do it in JAGS and if you forget to give a prior for sigma, I think JAGS gonna give you like error message to ask you to do something extra to make sure that you have it. So that will be another mechanism to make sure that you're doing things right. Okay, all right, good. So it's a little bit more complicated, as you can tell, but that is mostly, I think, coming from the fact that the race categorical predictor has 6 different levels, so it produces 5 different slopes. Okay, and then that makes the whole form a little bit more complicated. Okay, so let's take a moment. Okay, what does beta 0 mean in my mean in this equation? So this 49 is the same as 47 from before. What does the regression coefficient beta 1 mean? And what about the expected outcome of a CU with Native American reference person living in rural area with standardized log income equals to 1. Okay, so this is just some practice to make sure that you fully understand what we're doing with this mean equation in number 49. So this is on page 67 for remote students, and let's spend about 2 minutes on this before we move on to the estimation process. All right, so the intercept, as we know, will represent. Okay, so intercept is when all of the slope, I should say the x's for all of the other things taking value 0. So we're looking at when for a consumer unit, their standardized log income equals to 0, right? And then they are a urban consumer unit because their rural status is going to take 0. And all of the other non-reference level of the race taking value 0. So we're looking at a reference level to be a white person. So that's what beta 0 represents. That's the expected outcome for a consumer unit, which is urban and also having standardized log income equals to 0, and the reference level for the person, a reference race level for the race level of the reference person is white. So that's beta 0. Beta 1, as we know, is the coefficient for the standardized income. Okay, so what that means, as we know, is for every 1 unit increase for the standardized income variable, the expected outcome, I star, are going to change or going to increase or decrease depending on the sign of beta 1, on average about beta 1. And don't forget to say also that assuming all else held constant. So this is a multiple linear regression. So we need to make sure that whenever we're interpreting one slope itself, we're assuming that nothing else is changing about this hypothetical comparison that we do. Lastly, what about the expected outcome of a CU with Native American reference person living in a rural area with standardized log income? So for this, the mean will be beta 0, first of all. Okay, that's the intercept. Okay. And then we know that the standardized log income is 1, so beta 1 times 1, which will be beta 1. Okay. And we are also told that this CU is in rural area, so beta 2 times 1, because this will take value 1, because it's a rural CU. Okay. And lastly, we're looking at reference person race level is Native American, so I think that represents beta 4. So we're having this equation, which is beta 0 plus beta 1 times beta 2 plus beta 4 for this particular person, or I should say for the particular consumer unit. Okay, yeah. So of course, if I'm super curious about this last item, once I do my Bayesian inference, I can actually summarize, right? Because I'm going to get a bunch of draws for beta 0, beta 1, all of the betas actually, and also the sigma if I want. So I'm actually able to, get a 95% credible interval, get a posterior mean and median for the expected outcome for this particular combination of the predictors that we're curious about. And you can do that for all of the other ones as well. Make sense? Yes. All right, that's good. So, well, I think when this happens, when we're working with multiple linear regression with various different predictors, it's probably much harder to give subjective prior or conditional means prior, as you could imagine. So if you do have, I think, large number of data points, and if you don't really have strong prior belief to start with, it's always a good practice to give weakly informative prior, okay? And then you can just let the data and the model to drive the posterior inference. So we're gonna have what, 7? Let's see. We have 8 different betas, right? Beta 0 is the intercept, and then we have 7 slopes. And then don't forget that sigma. Like I said, sigma is always easy to be missed and all that. So you can see that if we assume independence, just like what we did before, we can give independent normal prior, okay, for each of the beta j's. J goes from 0 to 7 over here. And then for gamma, for sigma, 1 over sigma using gamma 1, 1 is always a good or useful weakly informative prior to get started. You might notice here that for the normal priors, I'm giving normal 0, 1 over here. Because at the very beginning on the unstandardized data, if you remember, we used normal 0 and 100, right, to represent a weakly informative prior. But that's on the unstandardized version. Okay, if you standardize it, then, well, normal 0, 1 is actually pretty weakly informative because after you do the standardization, center is 0 with standard deviation 1 is already representing a relatively weakly informative prior. Okay, so these are examples to start with, and you can always do this, right, in JAGS, and you can always change to other priors if you want to give it a try. That if it makes more sense for you to give in the prior specification. All right, so in order to get the JAGS script to work, so we do some pre-processing over here, and you can use the code later for that we posted on Moodle for your own practice as well. So don't forget that we need to standardize the log expenditure and log income. So we can use the scale function to do that, okay? And because later on it will be much easier, and we know that we start to have those indicator variable 0, 1s for all of the different levels, right, of the binary predictor as well as the categorical predictor. So if you want, you can use what we call like a dummy underscore codes, trying to create those dummy variables or the indicator variables. And it's coming from this fast dummies package. So if you install that package, load that package, and then also create that as well for both the urban rural variable as well as the trace variable. So you'll be able to get a complete column of those zeros and ones that you're able to get. So we're able to directly specify those beta 1 through beta 7 accordingly. Okay, so a bit tedious over here, as you can see, our sampling section of the model string is still following a loop. Okay, and our loop once again goes from 1 to capital N. So capital N is the number of observations. We're still using d-norm because the bulk of the main regression analysis over here, we're using the normal model. Okay. The mean is more complicated, as you can see right now, okay, because we have our beta 0 plus beta 1 times the first predictor, beta 2 times the second predictor, et cetera, until beta 7. Okay, so you kind of have to write out all over here. And you can see that we name all of the predictive variables like X income I, X rural I, and then later on X race B, B stands for black, X race N I think stands for Native American, yeah, and A stands for Asian, et cetera, So you will see that instead of, giving the whole matrix all of the x's that we're gonna pass it one by one as a vector, so it'll be easier to work with. And that's also the reason why we're creating those dummy variables early. Okay, so we can have each column one by one. And you can see that we have beta 0 to beta 7, so we get all of them as normal priors. You can determine the mu 0 and the g0 and all of them later as we pass the data. And lastly, we have our regular inverse sigma square as a gamma, and then we can track sigma as well. So the main change from what we had for the simple linear regression to the multiple linear regression over here is, well, back then we only had one predictor, and now we have, predictor variables actually have 7 over here. So we have 7 different axes going on. And then because of that, we have many more parameters to work with. But for the sampling model, it's still at the core, it's still this V norm. And then in the prior section, you are just listing all of the different priors that you're using. We're using normal everywhere pretty much, right? You just need to, write it down line by line because that's what you're taking in the sampling as well. So with that, as you can see, because now we're passing the x variables one by one, so we wanted to create one vector at a time for them as well. So we have our outcome variable still indicated as y, okay? And then we have our income and the rural, and then all of the non-reference level of our race. And then in the end, also n as the number of observations. So that's the pass the data and hyperparameter values and everything. So don't forget, we also have our normal 0, 1 prior everywhere. So we need to make sure that we pass them over. And then 1 over sigma squared follows the gamma 1, 1. So we need to pass that over as well. So this is relatively standard compared to before, but also a little bit more complicated compared to before because of the number of predictors that we're working with. But like I said, at the core, there's normal d norm everywhere in your model strings. And then the later ones are really just trying to match what you specify in your model. Okay, and also we can use the init function to get reproducible results, just like the stuff that we did before. So this is pretty standardized by now. And then lastly, this is the round.jags function, right? You get your model string, you get the number of chains, pass the data, let JAGS know which are the parameters you are tracking. So for us, beta 0, beta 1, up to beta 7. Okay, and don't forget sigma. I think sigma is always interesting and useful, especially later if you want to do prediction, you need sigma, okay? Because you need the sigma in the normal model to get your prediction. The adapt period, burn in, sample, theme, and also the initial values to get reproducible results. So this once again standard, I think, compared to before, and also a little bit more complicated. So of course, if you try to print, it's a lot going on, might not be easy to read the results and all that. But it's always useful, I think, first of all, to look at those betas, especially beta 1 through beta 7, because they are the slopes. Okay, you can check whether 0 is in the 95% credible interval or not, things like that, because if you ever do a hypothesis test over there, that will be the key. And you can see that most of them are pretty significant, I would say. Beta 1, always positive. Okay, beta 2, always negative. Beta 3, always negative as well. Beta 4 includes 0, beta 5, and beta 6, and beta 7. All of them seems to include 0 in their credible interval. And another thing we always try to look at, if you remember, is the effective sample size, just to make sure that at a first pass, it seems reasonable of the MCMC mixing seems to have been done pretty fine. Okay, so if you remember, if the effective sample size is really small, then that gives us worry of the MCMC that convergence has not achieved well enough. Okay, so overall seems fine. Remember, we use 5,000 draws in total. Some of them might seem to have a little bit higher autocorrelation, but overall everything is about 3,000 after we're taking into account of the autocorrelation and all that. And then you can pick a few if you want. Well, first of all, I should say, when you do the MCMC diagnostics, you have to check for all of the parameters. Okay, but for the interest of time and space, we only pick a couple over here. So beta 1, remember, is the slope for the income, okay, the log income. So over here, trace plot, autocorrelation plot, all look pretty good. And then earlier we saw that as well, beta 1 is strictly positive. Okay, so you're able to interpret the impact, I think, of beta 1. to the expected outcome. This is the one for beta 2. That is, I think, the slope for the rural indicator. Okay, so this is the rural compared to urban CU. What is the change? And we know that strictly, not strictly, a little bit, I think, mostly negative. So you can see that there is a negative effect, okay, from urban to rural, if you're thinking about the log expenditure. This is the one for sigma. We don't really need to interpret it, but you should check its MCMC diagnostics. And like I said later on, if you do predictions, sigma comes into play when you're trying to get a predicted value. So there are a couple of things we can do. So one thing, this is one example of coding exercise that you can actually plot all parameters on one graph if you ever want to do it. Okay. So sorry about the x-axis. I think everything is like messed up because I tried to squeeze everything into one graph. But nevertheless, this will give you an overview of, well, where are the betas usually? Okay, especially how they compare to 0 and all that. And then you can also see, for example, beta 7, I think, beta 4 and beta 7 as well. These few parameters, the posterior seems really flat. Okay. Real flat, meaning that, well, and I think around 0 as well. So this is very high level of uncertainty, I think, even in the posterior. And if you remember in the prior, we give all of them 0, 1. Okay. So you can always, if you want, pick one particular beta and try to plot its prior and the posterior, like what we did in the past, and see how things change. But at this level, I think for the multiple linear regression, our focus is really just looking at the posterior and then look at which one are important to pay attention to. So for example, beta 1 is much more peaked, okay, and quite different from 0, which is what we saw before. Okay, so you can probably tell from here that the log income will be a very useful predictor overall compared to some of the other ones, like the other levels of the race compared to the reference level of white. And I think this is the, I guess this is the better plot. Yeah, it's the same plot. Sorry, I guess I duplicated, but this is a little bit bigger, so we're able to see the outcome. Okay, I think I meant to suppress the output, but I forgot. But this is the code that you can use, which is available on Moodle, and this is the actual outcome over there. Okay, but nevertheless, we saw beta 4. Like I said, beta 4, beta 7, beta 6 are pretty flat in the posterior, and then yeah. So I didn't include sample code for doing, prediction and all that, but based on what we talked about in the simple linear regression, I think it's overall straightforward. The model is a little bit more complicated, but we covered how to write functions back then to do the predictions and all that for the simple linear regression. So you can also give it a try, imitate what we did before, and then update your code accordingly to do this for the multiple linear regression. Okay, so it should be straightforward, but you should reach out to me if you have questions and all that. Okay, so if you ever going to do Bayesian inferences, of course, like I said, you can do the expected outcome prediction. You can also do posterior predictive checks. Okay, so that involves simulating a large number of predictions, and then each prediction set is going to have the same sample size as the original data, and then you check how the model behaves. And of course, you can also experiment with several different priors to see if they have any kind of impact on the posterior inference. I was trying to highlight using weakly informative prior because for multiple linear regression, any other type of prior will be really hard to give because there are so many parameters and stuff going on. But if you do have very strong prior to give in your application, for example, for a project, I think it's definitely worth trying. And then you can always compare that with the more weakly informative prior that we covered. Okay, so that is what we have. Actually, this is the last topic of the entire course as well. So I'm gonna stop here, and the rest of the time, I think we have 15 minutes left. So I think you can use it for working on lab 5, which is on the conditional means prior, which is coming from the simple linear regression. Or I believe I gave feedback on all of the project proposals as well. So if you have any questions about that, I think now is a good time as well. And also next week we have the midterm exam. So if you have any questions about that, will be a good time for the rest of today's class as well. So next week, Wednesday, we're gonna have the in-class midterm, okay? And then Friday will be a regular lecture. which will involve some of the other exercises that we're gonna do. And then I think we have 2 more weeks left. The take-home part of the midterm 2 will be due the Tuesday after next. Okay, so I will release it sometime Wednesday next week, for example, when you're done with the in-class portion, and give you a whole week to work on the take-home part of the midterm 2. And then, well, you have the lab 5, as well as some other case studies that I will release later that you can team up by yourselves and do it. And then that will pretty much push us towards the end of the semester. Okay. All right, so I'm gonna stop recording here, and happy to answer any questions you have here and remote.